This is the 6th video in my series on alternating current. In this video, we are going to define a phasor. You'll find this topic along with others in my course entitled Basic Fundamentals of AC Circuit Analysis. You can access this and my other courses on my StanStore at this web address. So far, we have discovered that we can analyze AC circuits and currents and voltages using RMS values for resistive loads. That is to say, the AC currents and voltages are in phase. But that is not always the case. So we have another dimension to deal with, and in doing so, we have to develop and use another tool. This tool is called a phasor, which is a special type of vector. Vectors have two values, magnitude and direction. Phasors are vectors, but they also have a rotation. And usually it's at system frequency, and in North America that system frequency is 60 hertz. And that's what we'll be considering in our subsequent calculations. Okay, so let's build that tool. How exactly can we represent AC quantities of voltage or current in the form of a vector? Let the length of the vector represent the magnitude or amplitude or RMS value of the waveform, like this. The greater the amplitude of the waveform, the greater the length of a corresponding phasor. Before progressing further, we'll establish that all the sinusoidal wave phasors, voltages and currents, rotate at the same frequency. In the North American standard, the frequency of the system is 60 hertz or 60 cycles per second. So all the phasors, currents and voltages are all rotating at this frequency. Hence, they are separated only by a phase shift that can vary from 0 to 360 degrees. The angle of the vector, however, represents the phase shift in degrees between the waveforms in question and another one acting as a reference in time. Usually when the phase of a waveform in a circuit is expressed, it's referenced to the power supply voltage waveform, arbitrarily set at 0 degrees. Remember that phase is always a relative measurement between two waveforms rather than an absolute property. We will look here at A waveform with reference to B waveform. If there is a 0 degrees phase shift between these two phasors, A and B are in perfect step. They are in line with each other, so they kind of overlap. If there is a phase shift of 90 degrees, it could be that A is ahead of B, A leads B by 90 degrees, assuming a counterclockwise phase rotation. A phase shift of 90 degrees where B is ahead of A, this would also be indicated by these two phasors, where B leads A by 90 degrees. And a phase shift of 180 degrees means that A and B waveforms are basically mirror images of each other or are in the opposite directions. So let's list some of the characteristics of a phasor, and we will go on to develop how to analyze and calculate phasors. But for now, let's just talk about some of the characteristics of a phasor. A phasor can vary in length, which is equivalent to the phasor magnitude, which could be the phasors or the AC current or voltage magnitude, RMS value, peak to peak value. Doesn't matter which it is, the phasor's length is proportional to that quantity, we have to define what that quantity is if we want to work with it. But for now, we can say that phasors, the length of a phasor changes as its magnitude changes. All phasors rotate the same, and they're rotating at a frequency of 60 cycles per second, depending on the system. And in our system in North America is 60 cycles. I've slowed down the rotation here, otherwise if it was 60 cycles a second, you wouldn't be able to see it. So let's assume that it's scaled down here just for demonstration purposes. Phasors rotate about their tail. In other words, a phasor is represented by an arrow, and it is rotating about its tail. Phasors, all the phasors in the system rotate at the same direction. The standard that is usually adopted is counterclockwise. I will say this, but only once. It could be in a clockwise direction, as long as you maintain that sensibility and work with the understanding that phasors are rotating in a clockwise direction. However, the standards that we work with and the standards that I'll be working with in this course assumes the phasors are rotating in a counterclockwise direction, and they all rotate in the same direction. And phase angles of a phasor are relative. A phase angle cannot exist unless it's related to something else, and usually another vector. So phase angles are relative. The greater the phase shift in degrees between two waveforms, the greater the angle difference between the corresponding phasors. Being a relative measurement, like voltage, phase shift or phase angle only has meaning in reference to some standard waveform. Generally, this reference waveform is the main AC power supply voltage in the circuit. If there is more than one AC voltage source, then one of the sources is arbitrarily chosen to be the phase reference for all other measurements in the circuit. As in this diagram, phasor A phase shift is relative to phasor B. For convenience and ease of reference, we stop the reference phasor when it is at 0 with the horizontal, so it makes the relative measurements easier, or when the B waveform is at 0. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also, from time to time, be reviewing electrical products that, in my opinion, are worthy of paying attention to. This address will give you access to the supplier of the aforementioned type products. It is also a connection to obtain a free copy of my 24-page three-phase transformer workbook, which will serve as a quick reference and reminder of technical calculations that you may need. This address, of course, is case sensitive. I'll spell it out and make sure that you have it right. Everything up to the first number is lowercase. That is lowercase https://bit.ly/3, then uppercase U, uppercase G, a lowercase j, uppercase B, uppercase I, and lowercase g. One of those amazing and versatile products is the 𝐃𝐈𝐒𝐂𝐋𝐀 Delta Pro Ultra, which can be modified to suit any homeowner's needs, operating virtually silent, and when paired with the 𝐃𝐈𝐒𝐿 Smart Home Panel 2 is extremely versatile. The 𝐃𝐈𝐒𝐿 Home Panel 2 ties any and all of your standby power equipment together and will control them efficiently. It will even control your connection to the utility grid to make sure you're only using the least expensive power, switching to your standby power during those expensive time of use rates. In order to view the full range of 𝐃𝐈𝐒𝐂𝐋𝐀 products and obtain a free copy of my three-phase transformer workbook, check into this web address and simply provide your email address, which will guide you to browse the full extent of their products. There is no cost or commitment for viewing, and by providing your email address, it will allow me to keep you posted on future videos, courses, and 𝐃𝐈𝐒𝐂𝐋𝐀 products. Before I end this video, I want to repeat the connection to obtain a free copy of my 24-page three-phase transformer workbook, which will serve as a quick reference when working on my courses and quizzes. It is also a handy reference and reminder of technical calculations required in your daily job requirements. Finally, here is the link to all of my electrical courses, which are located in my stand store.